Welcome to the Math Detective Agency, where solving mathematical mysteries is our specialty. Today, we've been assigned a mission to recover a stolen item from this locked box. We have clues to unlock the box that involves pairs of expressions like this one. These expressions are equal, but how? To answer that, we're going to have to learn about the properties of numbers. These properties will give us the missing pieces we need in order to open the box and recover the stolen item. Let's get to work. To help us recover the stolen item, we have two objectives. First, we'll identify and describe the commutative, associative, identity, and distributive properties. Second, we'll apply those properties of numbers to justify why two expressions are equivalent. Before we can dig into our mission, though, we first have to understand what equivalent expressions are. Equivalent means equal, and an expression is a mathematical phrase. So equivalent expressions are math phrases that are equal to each other. But what makes equivalent expressions sneaky is that although they have the same value, they don't quite look the same. What's the secret to knowing if two expressions are equivalent? That's where the properties of numbers come in. These are rules that guide how numbers interact with each other. Let's take a look in our detective briefcase to see what they are. First up is the commutative property. This property is like starting a group chat with your friends. When it comes to the final group, does it matter what order everyone was added in? No! You can add friends in whatever order you'd like, and the chat will always have the same members in the end. To see the commutative property in math terms, let's look at the numbers 5 and 2. 5 plus 2 is 7. And what is 2 plus 5? Switching the order of the numbers. It's still 7. The order in which we added the numbers didn't matter. Do you think the commutative property also applies to multiplication? Test it out. Pick any two numbers. I'm going to use 8 and 4. Multiply the first number times the second number, then multiply those numbers in the opposite order. Record the answers you get in your guided notes and compare them. Pause here while you work. What did you notice about both answers? They were the same no matter which way you multiplied the two numbers. So the commutative property also applies to multiplication. Do you think the commutative property applies to subtraction? Well, let's think about it using our group chat example. If you're in a chat that has 6 total people and 4 people decide to leave, there will still be 2 people left. On the other hand, if you're in a chat with 4 total people and 6 people decide to leave, then there would... Wait, does that make any sense? Totally not. So the commutative property does not apply to subtraction. But how about division? Well, could our 6-person chat be split up into 2 smaller groups? Yeah, there would be 3 people in each smaller group. But what if we started with a group of only 2 people? Could we split that into 6 smaller groups? Nope. Again, there aren't enough people. Just like subtraction, order matters when it comes to division. So the commutative property doesn't apply. The commutative property states that numbers may be added or multiplied in any order without changing the value of the expression. But it does not apply to subtraction or division. The next tool in our Math Detective briefcase is the associative property. This one is like packing your suitcase for a trip. You can pack your shirts and pants together as a group and then pack your shoes. Or you can pack your shirts first and then your pants and shoes together. Does the way you group your items change what ends up in your suitcase in the end? Not at all.
We can test out the associative property using the numbers 3, 8, and 4. Here they're added together with different groupings. Pause while you simplify each expression and compare the answers. Remember that according to the order of operations, the group, or the parentheses, must be simplified first. All right, let's check it out. In the first expression, we add 3 and 8 first since they're in parentheses and get 11. Then we add 4 to that to get 15. In the second expression, we add 8 and 4 first to get 12, plus 3 also gives us 15. Changing the grouping doesn't change the value of the expression. Which other operations does the associative property apply to? Let's investigate. Pause while you simplify each expression here using gems to determine which pairs are equivalent. Just like the commutative property, the associative property also applies to multiplication, but not to subtraction or division, because when the grouping changed, the expression simplified to different values.
Next up is the identity property. Imagine you're saving money for a skateboard. If you have $50 saved and you either add or take away nothing, what's your savings? Right, still $50. How about if you multiply or divide your $50 by 1? Does your savings change? Nope, still $50. The identity property states that adding or subtracting 0 does not change a given number, and multiplying or dividing by 1 doesn't change it either. Last in our briefcase is the distributive property. A great example is shopping for school supplies. Say you're buying 6 notebooks for $3 each and 6 pens for $2 each. How could you figure out the total cost?
Since you're getting 6 of each item, you could add the price of 1 notebook and 1 pen and then multiply that by 6. 1 of each item would be $5. 6 times gives you $30 total. How is this process familiar? Right, it follows gems and simplifies the group first. How else could you find your total cost? Yeah, you could start by finding the cost for all 6 notebooks by multiplying 6 times $3 to get $18, and then find the cost for all 6 pens by multiplying 6 times $2 to get $12. Added together, this total is still $30. This method is known as distribution. Officially, the distributive property states that multiplying a number by the sum of 2 or more values is the same as multiplying the number by each addend separately. Both methods will give you the same result, but distributing will be especially useful when we start to use variables or unknown values.
Now that we've investigated all the different properties of numbers, it's time to crack the code and solve the case. We have 4 pairs of expressions, and we need to figure out which property makes each pair equivalent. The order of the properties will give us the code for the lock, and we'll be able to recover the stolen goods. Pause here while you identify the property that makes each pair of expressions equivalent. Return once you're done.
Check your code. In the first clue, both expressions show the value of 35 being unchanged by dividing by 1 and subtracting 0. These expressions are equivalent because of the identity property. So the first letter of the combination is I. In the second clue, both expressions add the same numbers and simplify to 16, but the parentheses move, changing the group. So they're equivalent because of the associative property. That means the second letter of the combination is A. The third clue shows one expression in which the sum of 2 and 7 is being multiplied by 4, and another in which the addends are being multiplied separately. Both expressions simplify to 36. This makes the expressions equivalent by the distributive property. So the third letter is D. And in the final clue, both expressions add the same numbers together, but the order of those numbers is different. Both expressions simplify to 21. They're equivalent by the commutative property, and the final letter in the combination lock is C.
Time to put our code into the lock. I, A, D, C. And aha! It worked! We've recovered an algebraic translator, a tool that reveals the mathematical meaning behind everyday language. No wonder this thing was stolen. It's so rare. But it's the perfect tool for us here at the Math Detective Agency. Thanks for your help today. I'll see you next time.